This is my Calculus 1 course. Today we're going to continue to learn optimization problems. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous class, we focused on area and volume problems. Today we're going to do some more area and volume problems, but we're going to do some other types of problems also. Get a picture of these steps here if you haven't already done that. And we're going to start with this problem. In the previous class, the problems that we dealt with, most of them had open intervals, and we didn't really have to consider the endpoints of the domain of the functions. But for this problem, we're actually going to have a closed interval, and we are going to have to consider the endpoints of the domain, because we're going to have a situation like this where the endpoints are part of the domain, and so you can see that if we're looking for a maximum value, this is the actual maximum value, and that yellow point does not occur at a critical number, and this blue point does not occur at a critical number. Remember, endpoints are not necessarily critical numbers. The critical number is going to be the location of the purple point. So let's get started here. It says a piece of wire 8 yards long is used to form a square and an equilateral triangle. That's important that it's equilateral. How much wire should be used for the square, and how much should be used for the triangle in order to enclose the most area? So we're trying to maximize the amount of area in the triangle and the square. So step number one, as usual, is to draw a picture. So we have a square. I'm going to make the sides x. And then we have an equilateral triangle, and I'm going to make those sides m. So that is step number one. We drew there's no constants in the picture, just variables. Step number two is to find an equation of the thing that you're trying to maximize. We're trying to maximize area. The area of the square is length times width, and the area of the triangle is base times height divided by 2. Now we know the length and the width of the square, that's just x and x, and we know the base of the triangle is m, but we don't know the height, so that's a problem. So what we need to do is we need to create an altitude here, and we need to consider this triangle here. Now we learned in my geometry course that an equilateral triangle, well, all the side lengths are the same. That's what it means to be equilateral. But if a triangle is equilateral, then it's also equiangular, meaning all these angles have the same measure. And because the triangle sum theorem tells us that the sum must be 180 degrees, you can figure out that each angle has to be 60 degrees. That's pretty obvious. So again, we learned that in my geometry course. And if we take out this blue triangle and analyze it, obviously this angle, as I mentioned, is 60 degrees, but we can assume that we're cutting this angle in half, so that would make this angle 30 degrees. And because it's an altitude, we're assuming that that angle is 90. So now we can go to our knowledge of 30, 60, 90 degree triangles. We have this theorem here that you should know by heart at this point. You can take a picture of that if you forgot that, but we did that a lot in trigonometry, and I think we reviewed it in pre-calculus. So if this side is omega, then this side is 2 times omega, and this side is omega times root 3. Now you can use the Pythagorean theorem if you want to, but you don't need to because it's a 30, 60, 90 degree triangle. Now, do you agree that this green length here is half of m? M is this pale green, so the bright green is half. So this length here, this bright green length, that's going to be m over 2. So omega is m over 2, which means that this length here is omega times root 3. So this length is m over 2 times root 3. So we did all that just to figure out what this question mark is in terms of m. This is the type of stuff that you're going to be expected to figure out in these types of problems. I know it's a lot, but so we have x squared plus m times m over 2 root 3 all over 2. So we have x squared plus, and we're going to simplify this. So that's a complex fraction. You should be able to deal with that complex fraction. We get m squared root 3 over 4. Okay, so at this point we have our equation for area, but we have a big problem. We have 2 variables on the right side of the equation. We're not allowed to have 2 variables on the right side of the equation. So we need to use this purple information to help us get this equation in terms of 1 variable only. And so we know that the total length, which I'll notate as LT, the total length of the wire, is the perimeter of the square, which is obviously 4x, plus the perimeter of the triangle, which is obviously 3m. And again, we know the total length is 8 yards. So that is 8. And this gives us a relation between x and m. Okay, so I'm going to solve for x because I don't want to plug in something here and have to multiply it by a bunch of by root 3. So x is equal to 8 minus 3m over 4. And it's probably going to be easier if we simplify that. So that's going to be 2 minus 3 over 4m. Remember, we can divide 8 and negative 3m by 4 separately. Okay, so now we can take that and we can plug it in for x in our equation because we want our equation in terms of just 1 variable. So now I can write the function a of x is equal to, actually it's going to be a of m. A of m is equal to 2 minus 3/4 m squared plus m squared root 3 over 4. So there you go. Okay, we're done with step 2. So again, step 2 is oftentimes the most challenging step. A lot of students don't get past step number 2. A lot of students make a mistake in step 1, and if they don't make a mistake in step 1, oftentimes they get stuck in step 2, but that's step 2. Now, do you want to use the chain rule or do you want to avoid the chain rule? Most students will probably say, well, I want to avoid the chain rule. If you want to avoid the chain rule, you have to expand this purple thing. Use foil and expand it. You can do that if you want, but I'm just going to use the chain rule because that's going to be easier, and I think it's good for us to practice the chain rule. So the reason we have to use the chain rule is because we have a blue function inside a bigger green function. See that? So we're going to take the derivative of the outside function, so that's the derivative of the outside function. That's step number 1 of the chain rule. Step number 2 is to keep the inside function. And step number 3 is to multiply all that by the derivative of the inside function. Do you agree that the derivative of the inside function, this blue function here, the derivative of that is just negative 3/4? Okay, and then we're going to add the derivative of this. Now root 3/4 is just a constant, so just consider this to be a big constant, so you're using the constant multiple rule. So the derivative of m squared is 2m, the 2 and the 4, they reduce to 1/2, so on and so forth. This is all just basic math. And if you want to slow down and do all that, and obviously you can just pause the video and figure that out if you're, but that's all just basic stuff at this point in your math curriculum. You should know all that. So I'm going to multiply the purple negative 3/4 with the 2, and I get negative 3/2 times 2 minus negative 3/4 m. And then we can distribute the negative 3/2, and we get negative 3 plus 9/8 m plus m root 3/2. So there you go. That's the derivative. So now we want to find the critical numbers of the derivative. The critical numbers are the numbers that make the derivative undefined or equal to 0. So there's no m values that are going to make the derivative undefined. But we can make the derivative 0. Okay, so we need to solve for m in this equation. And we could find an expression for the exact number, but that's going to require factoring the m out, because obviously we're not going to add these numbers very easily. So rather than confuse students with that, I'm just going to change to decimal form. So 9/8 is 1.125, and root 3/2 is 0.866. So now you can see all we're doing is just adding those like terms. You see the yellow like terms? You just add those together. And so if we do that, we get 1.991. Okay, and then we get approximately 1.50676, and that is yards. And technically we should have squiggly lines here, but it's not really that important. Okay, so at this point we need to we have our critical number, so that's the possible value, or the location, the m value, where you could have a maximum area. Now, before we use the first derivative test, let's look at the domain, because if we have a closed interval, we may not have to use the first derivative test, and I'll show you why in a minute. In the previous class, we had to use the first derivative test because we didn't have closed intervals. So, what is the biggest value, or let's start with the smallest value of m. M can actually be 0. So think about that. Think about the logic of the problem. If m is 0, what that means is that we're using all of the wire for the square. That's okay. That's fine. If you think about the context of the problem, that's actually allowed. Now we're using a bracket. You see that? That's different from most of the problems that we did in the previous class. M can actually be 0. That just means all of the wire is going to the square. Now, what is the biggest possible value of m? Well, the biggest possible value occurs if none of the wire is used for the square. So that's if x is 0. So if you go to this equation over here, you see that equation, let x equal 0. What does m equal? If x is 0, then m would equal 8/3. And again, we have a bracket. Because again, that's allowed. We can use all of the wire for the triangle. That's if m is 2 2/3 or 8/3. So again, here we have a closed interval, and because we have a closed interval, and we also have a continuous function. If you look at this this pale green function here, that's a continuous function. There's no m value that's going to make it undefined, or you can plug in any m value you want, you're going to get an output. So it's a continuous function, and it's a closed interval. So in that situation, you don't need to use the first derivative test. All you have to do is use this theorem here. If a function is continuous on a closed interval, then the critical numbers and or the endpoints are the locations where the absolute maximum and the absolute minimum value of the function could be found. So all we have to do is plug in the critical number into the function, and also the x values of the endpoints, which are 0 and 2 2/3, and then compare the value of this area, and whichever one is the bigger one, that tells you. So we don't have to use the first derivative test. But if you did use the first derivative test, what you would find is that this value, this yellow value here, actually leads to a minimum. We don't want the minimum, we want the maximum. So in this case, the critical number actually gave us something that we don't even want. All right, but let's go to the next page. And let's find our values of the area, and then we'll basically be done with this problem. So I'm going to copy that equation, write it there. So we're first going to analyze the function at the endpoints. So a of 0 we're going to find, and we're also going to find a of 8/3. Then we're going to evaluate the function at the critical number. So a of that yellow number down there. And so I'm going to color color code this. So we have 0 and 8/3, plugging that in there. And then we have our yellow number, plug it in there. So A of 1.50676. Okay, so plugging in 0, we have 2 minus 3/4 times 0 squared plus 0 squared times root 3/4. And that just equals 4. Okay, and that's 4 square yards. So now we're going to plug in 8/3. So we have 2 minus 3/4 times 8/3, all that squared, plus 8/3 squared times root 3/4. And you don't have to show all this, by the way. It's not really necessary to show all of this. You just have to you just have to plug it in. You can do this manually, or you can use your calculator for this. If you want to use your calculator, you can find these values pretty easily by entering this equation in. So I'm going to show you how to do that right now. So push the Y equals button on your TI-84 Plus. If you're using a different calculator, then you have to figure this out on your own. Push the Y equals button on your TI-84 Plus at the upper left. Y equals button at the upper left. Then you're going to enter this this purple equation in. And you can use the green alpha button and the Y equals button to find a fraction template. Now, you have to make sure that that your window has this domain here. So make sure, push the window button at the upper left, the F2 window table set window button. Press that and make sure that your window is something like this domain, or else you're not going to find the value. Then you want to push the blue second button at the upper left, and then the trace button, calculate trace button at the upper right. And then you're going to press enter on number 1 where it says value. And then you enter your value, which in this case is 8/3, and then press enter and it'll give you the number. So that is a very, very powerful tool. Very powerful tool to just calculate these numbers without having to actually do anything. So I'm going to do that and enter 8/3, and I get 3.0792 approximately. 3.0792 square yards. And so now we're going to plug in 1.50676. We're going to figure that out on the calculator. So press enter, the blue second button and the calculate button, and enter on value, and 1.50676, enter, and we get 1.73. I'll just say 1.74 square yards. Okay, so again, using this theorem over here, if you have a continuous function on a closed interval, the absolute maximum and the absolute minimum are going to be found at either the critical numbers, which is the yellow number, or the endpoints, which is the pink numbers. So all you have to do is look at these numbers. See these 3 numbers? Just look at those numbers and ask which one is the biggest one. We're trying to maximize the area. So in this case, this is something unusual. This didn't happen before. The maximum value actually occurs at an endpoint. So we want m to be 0. Remember those pink and yellow numbers? That's m. A is a function of m, right? So we want m to be 0. If m is 0, that means all of the wire is going to be used for the square. So we can say all of the wire should be used for the square. And that's it. That's our answer. So that's what this information told us here. And I'm going to color code that. This told us that all the wire should be used for the square, because that's the biggest number. 4 square yards is bigger than the green numbers. So there you go. So that was a problem where we had to look at the endpoints. And so now I want you to try a problem like that. And I noticed that I didn't write step number 4. I forgot to do that. So when we set the derivative equal to 0, that was technically step number 4. Okay, so you can take a picture of that if you want, and if you haven't already, go ahead and take a picture of these steps for the procedure. Also, you're not going to need the triangle stuff, but you will need this theorem, so get a picture of that. The problem that you're going to have is going to be easier. You're not going to need that triangle stuff, but you will need those formulas up there. So go ahead and try number 2, and when you come back, we'll do it together. Okay, we're back. Again, you want to compare this number and this number and this number. Okay, so if you got that right, excellent. Now notice that I used x for my independent variable. If you used r, your problem or your work is going to look a little bit different, but you should still have the same answer. So just be aware of that. Okay, so now we're going to try a different type of problem. This problem is going to be very different. This is a minimization problem. So let's look at this. This does not involve any geometry. There's no area or volume involved. And there's no geometry. So it says the product of two positive numbers is 336. If s is the sum of the two numbers, find the two numbers that minimize s. So no geometry involved, which means that step 1, which is draw a picture and label variables and constants, is not applicable. We don't even have to do that. Step number 2 is to come up with an equation of the thing that you're trying to minimize. We're trying to minimize the sum of two numbers. What are the two numbers? We'll just call them x and y. But we have two variables here, so how do we deal with that? Well, we're given this information here. The product of two positive numbers is 336. So if you multiply x and y, you get 336. So we can solve for y or we can solve for x, whichever one you want to do, it doesn't matter. And we get that expression there. And then we can take that expression and plug it in for y. And that gives us our function in terms of x only. So x plus 336 over x. Okay, so we're done with step 2. On to step number 3. We're going to find the derivative, but before we do that, let's change the form of this expression so we have 336x to the negative 1 power. Then we're going to find the derivative. We have 1 minus 336x to the negative 2 power. And remember, if you want to find the critical numbers, well, first let's just put this in a form that we can actually understand. And then if you want to find the critical numbers, you want to combine everything to one expression if you have a fraction. It's just easier to do it that way. So now we can use this expression in step number 4 to find the critical numbers. The critical numbers are the x values where the derivative is either 0 or undefined. So obviously if x is 0, then the derivative is undefined. But if x squared minus 36 is 0, the derivative is 0. And of course we have x is equal to plus or minus root 336, but we're not interested in the negative version of that because these numbers have to be positive. Do you see up here where it says the numbers have to be positive? Okay, so we have our critical number. Now we have to consider the domain. Before we do anything, we have to consider the domain because we want to know if we're going to use the first derivative test or if we're going to use that theorem that we talked about. If we have a closed interval and a continuous function, then we don't need to use the first derivative test. We can just check the value of the function at the endpoints and the critical number and then compare them and see which one's the smallest value so we can minimize. So let's look at the domain. We have a function of in terms of x. What is the smallest value of x? Well, x cannot be 0 because if you plug in 0 here, you get an undefined expression. So why is that? Why can't it be 0? Well, remember it told us the product of the two numbers is 336. So there's no way that x could be 0. And x cannot be negative numbers. But x can be positive numbers. So what that means is that we have an open interval. In the previous problems we had a closed interval. Now we have an open interval. And x cannot be equal to 0. But that's a bound. Okay, so now what is the biggest value of x? Well, the bigger x gets, the smaller y gets, as you can see from this equation. But x can just get bigger and bigger and bigger, and y will get smaller and smaller and smaller. It'll approach 0. Y will never equal 0, but there's no bound on x, really. I mean, it just can go on and on and on. There's no reason that x can't just go forever. And the same is true for y. The bounds of y are 0 to infinity also, but we only care about x because our purple function is in terms of x. So what this means is we can't use this theorem. We can't find the endpoints, or the value of the function at the endpoints and the value of the function at the critical number and just compare them. It doesn't work. So we need to use the first derivative test. And the reason we need to use the first derivative test is because that makes sure that we're not accidentally finding a maximum value at our critical number. This is our critical number. And let's get an approximation for that number. So that would be roughly 18.33. So we're going to test the derivative around that critical number. We can plug in 1, obviously we get a negative number. We can plug in 1,000, obviously we get a positive number. So the derivative changes from negative to positive. So again, that means that the function looks something like that. The slope over here, slope of the tangent line, which is the derivative, is negative because it's going down from left to right, but over here it's positive, so that's a minimum value. So what this told us is that that is a location. It's the location of a minimum. All right. And because the derivative is negative here and positive here, what that means is that it has to be the absolute minimum, because the function just goes up on this side and up on this side. So it's the absolute minimum. So what we have to do is evaluate that purple function. Actually, it says find the two numbers, so we don't have to evaluate it. So we found one of the numbers. So x is equal to the square root of 336. And then to find the other number, we just plug it into this equation here. So y is equal to 336 over x. X is root 336. And that's just going to be root 336, which we don't really have to approximate that, but if you're wondering how we did that, remember we just have 336 over 336 to the 1/2 power. Square root is 1/2 power. Then you just subtract these exponents and you get 1/2, which is root 336. So x is root 336 and y is the same number. Typically with these types of problems, the numbers end up being the same. So those are our answers. Those are the two numbers that minimize the sum. So I want you to try a problem like that. And for number 4, be aware that if x is a number, then 1 over x is the reciprocal of the number. Remember, you just flip it, because x is the same thing as x over 1. Reciprocal is 1 over x. You just flip it. So go ahead and try number 4. When you come back, we'll do it together. Okay, we're back. So x is 1 and y is 1. Those are the numbers that you can that minimize the sum. So if the sum if s is the sum of those two numbers, the two numbers that minimize that sum are 1 and 1 if the numbers are reciprocals of each other. Okay, so if you got that right, good. If you wrote your equation in terms of y, that's fine, but you should still get the same answers. X is equal to 1, y is equal to 1. You may have used different variables other than x and y, that's fine. Okay, so now we're going to go to a volume problem. It says a cylinder is inscribed in a sphere. The radius of the sphere is 3 millimeters. Find the dimensions of the cylinder that will result in the maximum volume of the cylinder. So let's draw a picture. So we have a sphere, and what it means for a cylinder to be inscribed in a sphere, that means that the corners of the base of the cylinder is touching the sides of the sphere. So what it means is the cylinder can just barely fit inside the sphere. It's big enough to just barely fit inside. And the radius of the sphere is a constant, 3 millimeters, and we're concerned with the radius of the base of the cylinder, and obviously the height of the cylinder. Those are the things we usually consider for cylinders. So we have our variables and our constants labeled on our picture. So that's step number one. Step number two is to find an equation of the thing that we're trying to maximize. We're trying to maximize the volume of the cylinder. So that's pi r squared h. Usually you're given this formula, but we want this side of the equation to be in terms of one variable. So how do we get that in terms of one variable? Well, we can't, because there's no additional information. There's nothing else here to really help us. But it does say the cylinder is inscribed in a sphere, as we mentioned, so that actually will help us. This is kind of a tricky problem. So what I'm going to do is I'm going to erase this green radius, and I'm going to draw the radius in a different way. I'm going to be kind of tricky here. I'm going to draw the radius down to the corner, or down to the side of the base of the cylinder. And so that's still the radius of the sphere, right? I'm then going to drop this blue line down, and do you see that blue triangle there? That blue triangle is something that we can use to get a relation between the height and the radius of the cylinder. Now I want you to notice that this blue length is h divided by 2. Do you see why that is? That's half the height of the cylinder. So there you go. That gives us our relation. Obviously we're going to use the Pythagorean theorem. So r squared plus h over 2 squared is equal to 3 squared. That's going to give us our relation. So it's easier to solve for r squared because we already have r squared. We don't want to have to deal with roots if we don't have to. So we have 9 minus h squared over 4. R squared is equal to 9 minus h squared over 4. So we're going to take that expression and plug it in for r squared. So then our volume formula, written in terms of h, is equal to pi times 9 minus h squared over 4 times h. Okay, so now if you want to, you can put the pi and the h together. You don't have to show that step, but it sometimes confuses students when you have a blue number on the right and on the left. So if you put those together and then you use the distribution rule, multiply that by 9, multiply that by this, because you don't want to keep it in this form, because then you'd have to use the product rule. So we have 9 pi times h minus pi over 4 times h cubed. So there you go. That's step number 2. So again, step number 2 is obvious, oftentimes the most difficult step. So now we are going to find the derivative of the function. And remember, 9 pi is just a constant. Okay, so we have the derivative. On to step number 4. What h values make the derivative undefined? There are no h values, but there are h values that make the derivative equal to 0. And if you solve for h, you end up with plus or minus root 12, but we don't care about the negative version of that because obviously the height cannot be a negative number. Okay, so I think we might be able to just leave h as root 12. We'll see what happens. We have to look at the domain to have a better understanding of what exactly is going on. Do we have an open interval or a closed interval? That's going to tell us how we proceed. So what is the smallest value of h? Well, if the cylinder just gets shorter and shorter, then it would look like this. As h gets smaller and smaller, then it would look like this, right? And then it would just get so small that it would basically just disappear, and h could be 0. If h is 0, then what is the volume? The volume is just 0. Plug in h, you get 0. So is that allowed? Well, there's no reason that h could not be 0. There's no reason the volume could not be 0. In this particular case, that's just because of the way that the function is defined. Now, in other situations, you might define it in a way where h cannot be 0. It just depends on the restrictions on the problem. In the previous class, we had restrictions that made it to where sometimes a dimension could not be 0 because it would conflict with other information. But in this problem, there's no reason that h can't be 0. It just means that the cylinder, the volume of the cylinder is 0 because there is no cylinder. Again, in the previous class, we couldn't do that because there were restrictions that prevented us. If you want to go back and look at that class, you can see why. But these little nuances make these problems very difficult, like I said. Now, what is the biggest value of h? Well, the biggest value of h occurs if you go the other way. If you make h really, really big, or just maximize h, then the cylinder starts to close inwards like this, to the point where it just disappears. And if it disappears, that means r would go to 0, right? So if you look over here, if r goes to 0, then what would h be? H would have to be, well, we just have to solve that equation, basically. So let's write this down here. So we have 0 squared plus h squared over 4 is equal to 9. And then h would be equal to 6. Actually, plus or minus 6, but again, we don't care about the minus 6. So if r went to 0, then h would be 6. That's the maximum value. Again, the volume would just be 0 in that case, you see. So with both of these pink bounds here, the volume of the cylinder would just be 0. Now, the big question is, do we have to use the first derivative test, or can we use this theorem here? Do we have a continuous function on a closed interval? And the answer is yes, we do. We can use this theorem. It's a closed interval. We have brackets. It's a closed interval. And we have a continuous function. Look at this purple function here. Is there any h value that makes it undefined? No. So it's continuous. So what that means is we can use that theorem. But in this problem over here, we found the value of the function at the endpoints and at the critical number. We don't really have to do that with this problem. And the reason is we can conceptually figure out what happens. We just figured it out. We know that if h is 0, then the volume of the cylinder is 0. If h is 6, the volume of the cylinder is also 0 because it just closes in on itself. So what you have here is a situation like this. Actually, like this. So here on the endpoints, your volume of the cylinder is 0, and this has got to be a maximum value. Now, why is it that we know it's a maximum value? Couldn't it be going like this? How do we know we're not going to get a minimum value? Don't we have to use the first derivative test? Well, not really, because obviously the volume of this cylinder is not going to go down. When h is 0, you have a collapsed cylinder, but then when h gets bigger, then all of a sudden the cylinder starts to expand, so the volume is not going to go down. It's not going to go into negative numbers. It's just going to get bigger and bigger, so it has to be this situation where you have a maximum value. So you can figure that out conceptually. You don't really need to use the first derivative test. But just be aware that if you're taking a test and you're expected to explain, then it would be hard to explain that in words. So probably what you would need to do is just use the first derivative test, and that would be the easiest way to explain it. But we've already gone over the concepts, and so I'm not going to use the first derivative test. So it says find the dimensions of the cylinder that will result in the maximum volume. So we already have root 12. So h is equal to root 12 millimeters. That's the height of the cylinder. And over here, we need to use that equation again to find r. So r squared is equal to 9 minus h squared over 4. And if h is root 12, then what would r be? Let me move this over a little bit. So r would just be, let me move that. Sorry, it's hard to find room on the page sometimes. So r would just be root 6. So h is root 12 and r is root 6. So those are the dimensions. And don't forget to draw your or write your units. Okay, so I want you to try number 6. And the most difficult thing is the tricky part here, where you have to somehow find a relation between the height and the radius of the cone. Now, I have a formula here that you can use for the volume of a cone, so use that formula. And again, the tricky part is finding the relation between h and r. If you get stuck, that's okay, but try to just give it an honest attempt. Don't just give up in 2 seconds. See what you can do. It's going to be, I believe it's going to be another Pythagorean situation. So try number 6, and when you come back, we'll do it together. Okay, we're back. So those are the dimensions of the cone that will maximize its volume. And if you're wondering how we came up with a relation between the height of the cone and the radius, look at this picture here. This yellow distance is the height of the cone, right? But this yellow distance here, that's also the radius of the sphere. So if you want the height if you want this blue distance here, that's going to be the height, the yellow distance, minus this leftover radius part. so h minus 2. So if you had some trouble with that, that's okay, but that's how you do that. Again, we didn't have to use the first derivative test because we just understood through logic that these endpoints, these pink endpoints here, they would produce a volume of 0 for the cone. So obviously they're not going to be maximum values. So the maximum value occurs in the middle of the domain. So if you got that right, excellent. Now again, if you're trying to explain to somebody why we didn't have to use the first derivative test, what you could do is you could say, well, the volume when you plug in 0 is 0. The volume when you plug in 4 is 0, testing the endpoints. So that kind of demonstrates to people why we proceeded the way that we did. And the critical number, if you plug that into the volume, you get a max. We don't even have to calculate it, we just know that that's what it's going to be. Same thing on the other problem. We didn't write it, but just to be thorough, you could show that when you take the AP exam, they're going to require you to explain everything. So we're just learning the concepts right now, but just be aware that they will require you to explain everything. So in this example, the critical number was root 12. So again, we know when we plug in 0 and 6 on the previous problem, we get 0, 0. And if we plug in root 12, we have to get a max. We just knew that. We don't really have to calculate it. That takes time and energy. And you would have to calculate it on the AP exam, the advanced placement exam again. But that's why you need to know how to use your calculator so you can enter this in and not have to do all the math, because the math just gets really tedious. Okay, so if you got that right, excellent. So on to the next problem. So this is a problem where we're going to minimize, and the algebra is going to be really intense on this problem. So I just want you to be aware of that. Now, a part of me doesn't really want to give you this problem because the algebra gets so intense, but unfortunately you will see these types of problems, not on the advanced placement exam. They don't put a lot of problems with really difficult algebra, but you may see this in some, if you take a calculus course, this does happen. The algebra gets really intense. And you have the tools that you need to solve the equation, but you may never have actually seen that exact equation. It's like if you learn how to ride a bike. Later on, many years after you learn how to ride the bike, you may encounter situations that you didn't encounter when you actually learned to ride the bike. But that doesn't mean that you can't use the tools that you learned when you learned how to ride the bike to figure out how to maneuver the situation many years later. When you find yourself in a different situation. Well, the same is true with algebra. The equation that we're going to encounter here is nothing that you've seen previously, but you can still use the tools that you learned to solve the problem. So I know that's not exactly fair, but that does happen in the math curriculum, and it happens in calculus. So I'm not doing this to try to torture you. I'm just doing this to prepare you. So let's read. It says there are two poles located 12 meters apart. One pole is 8 meters high and the other is 15 meters high. Each pole is stabilized with a wire connected to the top of the pole and a common point on the ground between the two poles. And we have a picture written for us. So in this problem they wrote the picture for us. Where should the wires be connected on the ground to minimize the amount of wire that is required? Okay, so step number 1 is mostly done for us, but we do need some variables. We need L1 and we need L2, the length of the wires. We're going to minimize the length of the wires. So step number 1 is actually done for us, so that's good. Alright? Step number 2 is to come up with an equation of the thing that we're trying to minimize. That's the total length of the wire, which is going to be length 1 plus length 2. Problem is we have two variables over here. We're not allowed to have two variables, so how do we deal with this? Well, we use the Pythagorean theorem. We're going to define a new variable. I'm going to define this length from here to where the wires connect on the ground. I'm going to define that as x. And if that's x, isn't it true that this length over here would be 12 minus x? Is that correct? Obviously, I mean, this length is 12, the yellow length is 12, so 12 minus x would be the leftover blue area, right? Okay, so now I'm going to consider this blue triangle. Notice that that blue triangle is a right triangle because we're assuming that the pole is obviously going straight up. And I'm going to consider this yellow triangle. So we're going to use the Pythagorean theorem, and we're going to consider the blue triangle first. So that tells us x squared plus 15 squared is equal to L1 squared. That's using the blue triangle. Using the other triangle, we have 8 squared plus 12 minus x squared is equal to L2 squared. So if we solve for L1, we get plus or minus root x squared plus 225. But of course we don't care about the negative version of that. So now we have an equation for L in terms of x. This is helping us get everything in terms of one variable. Remember, that's oftentimes the hardest part of the problem. Over here we're going to get 64. Well, actually, let's just solve for L. L2, that is. So L2 is equal to plus or minus root 64 plus 12 minus x squared. And of course we don't care about the negative version of that. I'm just writing plus or minus because I want you to get in the habit of writing plus or minus. It's one of the biggest mistakes that students make in certain problems is they forget to write a plus or minus. We don't have to use the plus or minus in this problem, but we still need to remember when you square root both sides of an equation, you get a plus or minus symbol. So now we can go over to our equation and we can write it in terms of just x. So the total length of the wire is equal to the square root of x squared plus 225 plus the square root of 64 plus 12 minus x, and I'm going to provide some more room here. 12 minus x squared. So there you go. We finished step number 2. So again, as you can see, step number 2 is, well, that was pretty involved. So why don't you look over that, make sure you understand everything that we did. So now we need to find the derivative, and this is where things are going to start to get messy. Now, before we find the derivative, we need to consider those roots in exponential form. Just helps us to find the derivative. Now, a lot of students might say, should you just expand this? You could expand it, but for reasons that we'll talk about later, we're going to keep that in that form. So now we're going to find the derivative of the function, and we have to use the chain rule. So we found the derivative of the outside function in green, we kept the inside function in blue, and then we multiplied by the derivative of the inside blue function, which is the purple expression. We have to do the same thing on the other expression because we have a function inside another function. In fact, we have to use the chain rule twice. So unfortunately that happens. We found the derivative of the outside function, and we kept the inside function, and then we're going to multiply by the derivative of the inside function. But if you look at the inside function has a function within a function. So you have to use the chain rule again. That's why it's called the chain rule. So 0 plus 2 times 12 minus x to the 2 minus 1 times negative 1. And we need an extra parenthesis there. So we had to use the chain rule again. And so the derivative of the outside function, and we kept the inside function, and we multiplied by the derivative of the inside function. Okay, so let's check this over, make sure we did everything correctly. Everything looks right. So now we just have to simplify this. So these two, the 1/2 and the 2, they're going to multiply, cancel each other out. You don't have to show every step of this. I'm going slower than you need to go. So we have the -1 and the 2 here. That's going to be -2 multiplied by 1/2 is -1. So that would change that to a negative. And then we have 64 plus 12 minus x squared to the -1/2 power times 12 minus x. So I'm trying to go slow here so you can see what's going on. So at that point we have, again, this is the derivative of the total length of the wire. So we have x over the square root of x squared plus 225. We have a negative exponent, so it goes down to the denominator, and it's a fraction exponent, so it becomes a root. And so over here we have 12 minus x over the square root of 64 plus 12 minus x squared. And it looks like that's it. So the reason we put it back into root form is because we want to have an idea of what we're looking at. Obviously, if it's not in root form, we don't know what in the world we're even looking at. Okay, so let's double check that. Everything looks right. Okay, so now we need to go to step number 4 and find the critical numbers. Now this is where the algebra tends to get really out of hand on this problem. And look over this and make sure that you understand everything that we've done so far. But we're now going to find the critical numbers. But remember, to find the critical numbers, you want to combine fractions into one expression. That helps us figure out where the derivative is undefined and where it's 0. So I'm going to show you exactly how we're going to do that. We have to get a common denominator. And this is where things get kind of scary for students. It's just basic algebra, but it's very messy, so it seems very, very scary. So what I'm going to do to find a common denominator is I'm going to multiply both sides of this fraction by square root 64 plus 12 minus x squared. And I'm going to multiply both sides of this fraction by square root x squared plus 225. Because I have the square root, I don't really need parentheses. You don't have to show this. You don't have to show the green and the orange. You can just do it. But once we do that, we'll have a common denominator. We can add these expressions together. So that is our denominator for that fraction. And we have to use parentheses on 12 minus x. If you don't, your expression is going to be wrong. It's going to be misinterpreted. And we have the same denominator over here. So look over that and make sure you agree with the logic behind that. We now have a common denominator. You see this green denominator in both the fractions? It's a common denominator. So also I probably should use purple parentheses here, or else that's not technically correct. Okay, so let's look over this. Make sure we have everything right. Okay, so now we're going to combine to one fraction. So we're going to subtract the numerators, I guess you would say. Obviously, we don't have like terms here. So we get that expression, and we add them together. And by the way, all of this stuff is equal to L prime of x. I should have written that. Okay, so we want to figure out the critical numbers. Those are the numbers that make the denominator 0, or they make the numerator 0. Now, the reason that we kept this 12 minus x squared in that form is because we can see that there's no x value that makes the denominator 0. So that's kind of a relief that we don't have to set this equal to 0 and solve it. Because it doesn't matter what x value you plug in here, you're not going to make this expression 0. Think about that. If you plug in 0 for x, or square root 225, or negative square root 225, it doesn't matter if you plug in a positive, a negative, or whatever, you're not going to make that 0, because when you square x, it becomes a positive number. Same thing here. When you square 12 minus x, it makes a positive number. So you can't add a positive number to a positive number and get 0. So you can't make the denominator equal to 0. It's not possible. So that denominator cannot be 0. So I'm going to write cannot be 0. But the numerator, we want to know if that's equal to 0. So that's the whole problem right there. Is figuring out when the numerator is equal to 0. So we'll try to fit this on the page. So we're going to set that equal to 0. And here's where the algebra gets really intense. This is what I was talking about. You have the tools that you need to solve this equation, but you may have never seen this equation. And so this is where things get kind of intense. It may not be exactly clear how to solve the equation. But what we're going to do is we're going to add this term to both sides of the equation. So we're going to put it on the other side. So we have 12 minus x times the square root of x squared plus 225. Square root of 225. And at this point, we don't want those square roots. We don't like the square roots. So we want to square both sides of the equation to get rid of the square roots. And we're going to have to use exponent rule number 3 for those who know the numbers in my intermediate algebra course. So I'm going to square both sides. Exponent rule number 3 says a number times another number to some nth power is equal to the first number to the nth power times the second number to the nth power. Alright, that's a tool that we learned. And so what that tells us is that we get x squared times 64 plus 12 minus x squared. When you square a square root, it just gets rid of the square root, right? And if you square x, it becomes x squared. Same thing here. We have 12 minus x squared, but then when you square the square root, you just get rid of the square root. Alright? Okay, so at this point, we're going to distribute the x squared to 64 and the 12 minus x squared. So we have 64x squared plus 12 minus x squared x squared. And then we're going to distribute the 12 minus x squared. So we have x squared times 12 minus x squared plus 225, 12 minus x squared. Okay, now notice that we have some terms that are the same. So that's really good news, because those can just cancel out. We just subtract that term from both sides and we end up with 64x squared is equal to 225 times 12 minus x squared. Okay, so now we have to do something tricky again. We could expand and we'd probably end up with a quadratic equation, but we don't want to deal with quadratic equations if we don't have to, so I'm going to do this an easier way. And the reason I'm going to do it an easier way is because notice that these are all perfect squares. So because they're all perfect squares, I'm going to square root both sides of the equation. But remember, when you square root both sides of an equation, you have to write plus or minus. Now, you can write it on this side, or both sides. It doesn't really matter. I'm just going to write it on both sides because we have variables on both sides. And now we have to use the rule, the nth root of a number times another number is equal to the nth root of the first number times the nth root of the second number. So that is that principle there. Now, students like to claim that they've never seen that before, but if you're coming from my curriculum, you've seen that 1,000 times. That's all we're using is that formula that we've used 1,000 times. You may be a little rusty on that, but now in this case, n is actually 2, but we don't see the 2 because remember, when the index is 2, we don't write it. It's square root. So what that does is it square roots 64 to become 8, square roots x squared to become x, and it square roots 225 to become 15, and it square roots 12 minus x squared to be 12 minus x. But we have a plus or minus, so there's actually two equations. Okay, now if both of these are positive, because what we're doing is we're taking a number here and a number here and we're squaring them, and then we're getting these numbers. So what that means is that this number could be positive and this number could be positive. Both of the numbers could be negative, and those two situations are going to be here. But it's possible one of these numbers could be negative and the other could be positive, or this number could be negative and this number could be positive. In that situation, we have to put a sign on one of these, or a negative sign on one of these. It doesn't matter which side, because I can multiply both sides of this equation by -1, and it just puts the negative on the other side. So putting a negative on one side, that represents both scenarios when you have the negative on this side or this side. I know that's very confusing. Again, this type of stuff just comes out, and calculus professors they just expect you to know what's going on, but most students don't. So I'm just giving you an example of how things can get out of hand, and sometimes it's just something you have to deal with. But I want you to know that I'm not going to give you any problems on a test that you have not already seen. So this may be a very difficult problem, but I'm not going to give you any other types of problems that'll just have this stuff pop up out of nowhere. Okay, so now we just have to solve those two equations. And so we get 23x is equal to 180, and x is equal to 180 over 23. Over here we get x is equal to 180 over 7, and we need to come up with approximate values. So 180 divided by 23 is approximately 7.826, and the units are meters. And over here we have approximately 25.714 meters. Okay. Now we need to consider the domain of the function. What are the possible values of x? Well, you need to use a combination of the picture and a combination of equations to figure out what the domain is, but this picture is going to be enough for us to find the domain of x. X is this purple number down here, right? So what is the smallest value of x? Well, x could actually be 0. If x is 0, then that would mean that this wire here would just be going straight down the pole. I don't know if that would really stabilize the pole very much, but the problem doesn't tell us that that can't happen, so x could actually be 0. And that's a bracket. What is the biggest value of x? Well, if this point moves all the way to the smaller pole, then that would mean x would have to go to 12. And this wire here would just be going straight down the smaller pole, because the point where the two wires connect would just be at the base of the small pole. So x could actually be 12. Again, these are the little nuances in these problems which make things very difficult. Okay, so that is the domain. So we actually need to consider the endpoints, because that theorem that I showed you, that applies. We have a continuous function. Because x is squared in both of these, there's no x value that you cannot put into that function. It's a continuous function, and we have a closed interval, 0 to 12. So we can use our theorem that says that if a function is continuous on a closed interval, then the location of the critical number or the location of the endpoints, they will lead us to a maximum or minimum value in that interval. So we need to use this equation here, and this is a perfect situation where your calculator would come in handy, because having to do this manually would be very, very difficult. We want to calculate the length of the wire, the total length of the wire. For each one of these points, we're going to plug in 0, and we're going to plug in 12, and calculate the length of the wire, and then compare to the value we get when we plug in the critical point, or the critical number. That's if you plug in, and by the way, I forgot to mention, see these two numbers up here? We have two critical numbers, but one of them is not in the domain. So we need to cross that out. Alright, so that's obviously not going to be, it's not in this domain here. So we only care about that yellow number there. So 7.8, actually we could just plug in 180 over 23. I guess I'm just going to write the yellow number, 7.826 approximately. Okay, so then we just need to calculate those numbers, but again, it's going to be a lot easier to enter this into your calculator and let the calculator do the work for you in a lot of these cases, but it might be easy to calculate the endpoints. So let's just see what we get here. 0 squared plus 225 plus root 64 plus 12 minus 0 squared. So we get 15 plus root 64 plus 144. That's 208. And so when we add those together, we get 29.42, and that is meters. So when we plug in 12 to that red equation, we get the square root of 12 squared plus 225 plus the square root of 64 plus 12 minus 12 squared, and we get the square root of 369 plus the square root of 64, which is 8. So calculating that, we get approximately 27.2 meters. So but again, it's a lot easier to just enter the equation into your calculator and then use the blue second button and the calculate trace button on your calculator. Okay, and another reason it's good to do that is you can enter the actual number in. It's a lot easier to enter the number in. So push the y equals button on your calculator if you want to do that, and enter the equation in, and then push the graph button. And if your graph doesn't have this domain, make sure that the window is showing that domain. So press the window button at the upper left and enter those in. So now push the blue second button and then the trace calculate button at the upper right, and then enter your value, which I'm going to enter the exact number, 180 divided by 23. That's this yellow number. See this number up here, 180 divided by 23. Then I'll get a more precise number. Enter. And so I get 25.942 meters. So now I want you to compare this value, and this value. Which one's the smallest value? Again, read the problem. We're trying to find the point to connect those two wires in the ground that will lead to the least amount of wire being used. So you want the least amount of wire, and that's going to be this value here, 25.942 meters. So we need to connect the wires at a see this yellow 7.826. We need to connect the wires 7.826 meters from the tallest pole. So connect the wires on the ground 7.826 meters from the tallest, or we can say taller pole, and that's the answer. That'll maximize the amount of wire used. Okay, so again, I'm not trying to torment you by giving you a problem like that, but you just need to know, you need to be aware that sometimes with calculus, they give you algebra problems like this, and you're just expected to be able to use the tools that you learned in previous classes to kind of maneuver your way through this. So again, I'm not going to give you a surprise problem that requires algebra like that, a problem that you've never seen. I'm only going to give you problems that you've seen before, so don't get too anxious about this problem. Now, you don't have to take this long to do this problem. You can go very, very quickly. You don't have to show every single one of these steps. If you know what you're doing, you can go through this a lot faster. And just be aware that there was a lot of things that we did here to avoid having to solve a complicated equation, so you want to use those tools. Now, we don't have time to do, or we don't have time for you to do a problem like this in class. I don't want to make you go too long in this class today, but I will give you a homework problem, and you can use this problem to help you do the homework problem. So that said, if you want to get screenshots of all the work that we did today to help you with the homework and to study for tests, go ahead and do that now. Here's screenshot number 1. And here's screenshot number 2. And I want to make sure you get a chance to take a picture of these. I don't know if you'll need the 30, 60, 90 degree triangle theorem. Actually, I think you will need it, if I remember correctly. But you would definitely need this theorem here. And here we have the next screenshot. And the next screenshot. And the next screenshot. And this problem, like I said, will be very helpful for you when you do the last problem on the homework. The last problem is going to be like this. And so if you get stuck, you can just use this to help you. It's going to be almost exactly the same type of problem. So now let's get pictures of the homework. Remember, if you don't do the homework, you learn nothing in this entire course. So get this, get a screenshot of this first screen here, the first 2 pages. Here's a second screenshot. And this is the problem that's going to have a lot of algebra. And again, I'm not giving you this problem to torture you. I'm just giving you this problem because you very well may see a problem like this at some point in your math curriculum. So I just don't want you to be caught off guard if you see that. Again, if you get stuck, you can use the problem that we did in class. Now here's the answers to the homework. So get a screenshot of those answers. And see here, it says show all work. So you need to show everything that you do, and it needs to be organized. And you need to keep a record of your homework in your binder, remember. So get that homework done, and I'll look forward to seeing you in the next class.